And he will talk about fractional neural networks approximation and using algebraic function-based Banach space values ordinary, also neural networks. Thank you, George.
Thank you very much, Eulalia, for introducing me. I would like to thank everybody for coming to my talk, and I also would like to thank the organizers for inviting me. Okay, my main approach in research in the last 30 years is trying to apply fractional calculus in other areas of mathematics like inequalities and approximation theory and neural networks today here. So today I'm going to talk about approximation, ordinary and fractional approximation in neural networks. And I'm doing it more general for Banach space valued functions. Okay, the neural networks is part of artificial intelligence, as you know, and there are two major directions. One is in computer science with mainly talking, less mathematics. And the other direction is in mathematics, dealing with also differential equations, partial differential equations, and approximation theory in my case. So the whole thing started in 1943 by the very important paper of Magulo and Pitts, a logical calculus of the ideas immanent in nervous activity relating to mathematical biophysics, 1943. So trying to make a model of the brain and trying to do mathematics with that. So I'll give a little bit of history in my research. When I started my career here at the University of Memphis, 1986, my colleague, Stan Franklin, he gave me to referee a very famous paper that became afterwards by George Sibbenko, Russian theoretical engineer, mathematician George Sibbenko, approximation by superpositions of a sigmoid function. So approximation of functions, continuous, measurable by superpositions of sigmoidal functions. That established theorems qualitative of approximation of functions by superpositions of sigmoidal function. No rates of convergence, no inequalities, not specific operators, but it started the mathematical, I would say, theory of neural networks, approximation theory. Other guys also were contemporaries like Hornick, Calvert White, Baron, etc. Then in 1992, for the first time, two French theoretical engineer mathematicians, Pierre Gardalaguet and Guillaume Jouvrad, they wrote down operators with specific coefficients. So they gave a particular form of neural network operator approaching the function f, which is continuous, etc. But still no speeds, no inequalities, no rates. In 1997, I was the first to put this approximation by Gardalaguet-Jouvrad operators in quantitative form. So giving inequalities, giving with modulus of continuity, rate of convergence, etc. That was in Journal of Mathematical Analysis and Applications, 1997. In 2000, I gave the corresponding multivariate theory that was published in Journal of Computers and Mathematics with Applications. And since then, I work on that topic in and out, of various years. I produced in 2011 this little monograph of intelligent systems approximation by artificial neural networks, where the activating function was the standard sigmoidal 1 over 1 plus e to the minus x. And then I wrote many other papers, resulting in a thick monograph, 2016, on the matter. I was inspired also by the important work by Chen and Chao, dealing with quasi-interpolation operators. Okay, today, I'm gonna talk about algebraic function-based Banach space value ordinary fraction neural network approximations. Why algebraic? The sigmoidal function now is algebraic. That means it's a solution of polynomial. That means can be formed by 4 basic operations: addition, multiplication, division, etc., subtraction. So that is easier for calculations. Usually are transcendental, I've done with the basic sigmoidal and also the hyperbolic tangent, etc., arc tangent, all kinds of things. Okay. So the generator algebraic function is what you see, phi of x, little phi of x over square root, 2m root of 1 plus x to the 2m. M, natural number, so 2m is even, x, real number, is a sigmoidal type of function which is strictly increasing. Okay, that's the generator. Okay, let's discuss about the properties of that function. Has indeed nice properties. First of all, phi of minus x is minus phi of x is odd. Phi of 0, 0. The derivative is positive, so it's strictly increasing on R. And the derivative of phi is phi of minus x. The limits as x goes to plus infinity is 1, to then minus infinity minus 1. And here comes the activation function. Uppercase phi, 1/4 phi of x plus 1 minus phi of x minus 1. This came after a lot of experimentation. What's the most appropriate? To fulfill the following properties. First of all, is even. Okay? Symmetric to the y-axis. Then is positive all the time. Phi of 0 is 1 over twice 2m square root of, root of 2. The derivative is what you see, relation 5, and is greater than 0. The derivative is negative for x positive. So phi is strictly decreasing on the positive real axis. By symmetry, phi is increasing on the negative real axis. And the derivative of phi is 0. Furthermore, we get that the x-axis is horizontal asymptote of uppercase phi. So phi is Bell symmetric function with maximum phi of 0 1 over twice 2m root of 2. So that's the kind of activation function we want to have, and it's typical in approximation theory by neural networks. To make a Bell symmetric with respect to the y-axis. Now, further important properties. Partition of unity. Sum from minus infinity to infinity, uppercase phi x minus I is 1. Okay? So is analyzed, I break this infinite sum into infinite sums, and then using telescoping sum, and then the properties of that phi of plus minus infinity is plus minus 1. Adding the, so I get this thing here from minus infinity to infinity, phi x minus I, phi x minus 1 minus I2. And then this is true for every x, therefore it's true for x plus 1. Adding the 2 gives 4, divide by 4, we have the theorem. So one more time to see the theorem. The first theorem of the kind is this, the partition of unity of the activation function. Okay, furthermore, we are going to use that now. Phi of infinite sum phi of I minus x is 1 for every x, therefore infinite sum phi of I plus x is 1 for every x, and again the same thing. And finally, that's the nice thing here, you get that the integral from minus infinity to infinity phi of x dx is 1. Proving, I mean, it's very easy to prove that now, having all the machinery, proving that phi of x is a density function on R. Okay? Density function on R. Okay, let me present a couple of more properties, very important properties. We have a parameter alpha, parameter of speed, alpha between 0 and 1. And we consider natural numbers n so that n to the power 1 minus alpha is greater than 2. Then the infinite sum from minus infinity to infinity phi n x minus k over all k such that absolute value n x minus k is greater or equal n to 1 minus alpha is less than 1 over 4m parenthesis n 1 minus alpha power minus 2 to the 2m. So the proof is done using real analysis. I mention again phi. Consider x greater or equal 1. Apply the mean value theorem. And then from there derive that phi of x is less than this function here, 1 over 2x 1 plus x minus 1 to m to the power 2m plus 1 over 2m for every x greater or equal 1. And then working in an elegant way, exchanging sums to integrals, infinite sum to integral, and calculating the integral, upper bound the integrand, and finally have the desired result. So still this is machinery for my approximation theory to be presented. So see that one more time. Infinite sum n x minus k greater or equal n to 1 minus alpha, phi n x minus k is less than that. Okay? Of course, as n goes to infinity, this goes to 0. The whole thing collapses to 0. Okay? And then another important piece of machinery. By the way, this symbol is the integral part, the least number before the number, integer, sorry, before the number, and the, excuse me, the largest integer before the number is the integral part, and the smallest integer above the number is the ceiling of the number. Okay, the next thing to prove that is 1 over sum phi nk minus k, finite sum now, finite sum from na ceiling to nk integral part is smaller than this number. Okay, is proved by reasoning, you know, real analysis and, you know, basic things. Nothing really extremely difficult, you know. Okay? So we have an upper bound for this quantity here. Okay? All right. Next. 1 second. Excuse me. Okay. Okay. Let X nor be a Banach space. Now starts introducing my operators. Let F continues from A, B to X with n in n such that ceiling NA is smaller than the integral part NB. So for sufficiently large n, this is true, always true, for sufficiently large n, no matter what A and B is, whatever small. Okay, so if we define the X value linear neural network operators. Please take a look at it. So we're going to have finite sums and also infinite, two kinds of operators. Let me tell you what is the eventual goal. I mean, of course, is to present approximation by these operators. These are neural network operators. But what you're going to see is by adding ordinary differentiability using methods of fractional calculus, we achieve higher speed of convergence. Okay? So you compare approximation for just continuous function, approximation for one-time continuous differential functions, and by using fractional calculus methods without any assumption or boundary conditions or initial conditions, we achieve higher order speed. You will see that at the end of the talk. Okay, so the first operator we introduce is what we see there, is normalized. You see here in the bottom, you see the sum. For my early years of investigations, I did not do that. I did not divide by this sum. And my approximations were not as good. So finally, I came up to this idea to normalize. So you see in this operator, two kinds of things are involved. The activation function and the function under approximation. And you have this particular coefficient. Resembles a little bit Bernstein operators. Okay? So this is univariate theory. I'll also later follow with multivariate theory. But you need to start with the univariate theory. Okay. One thing we see, is that the operator maps f into continuous functions. If I had functions real valued, the operator is a positive linear operator. Clear. I define this auxiliary operator an star, this sum. So the an is written an star over the sum of normalization, and then doing calculations, I have that an fx minus f of x, that's the error quantity we'd like to approximate, to estimate, is smaller or equal to this number times this auxiliary operator minus f of x times the sum, finite sum, which is same as that. So we estimate the right-hand side of this inequality. What we employ is the first modulus of continuity, which measures smoothness of the function. It has very nice properties. The main property is as delta goes to 0, this goes to 0 too, as long as the function is uniformly continuous. Okay, similarly defined for the space UBRX, uniformly continuous and bounded functions, also continuous and bounded functions, or just uniformly continuous functions. Okay, so this modulus of continuity goes to 0 if and only if, if you have F continuous or F uniformly continuous, is equivalent to that. Okay, now the operator, the x-valued quasi-interpolation neural operator is over the whole real line. The sum now is infinite sum. Okay, infinite sum. In other papers, I have other coefficients here or other activation functions. This one is x-valued, Banach space valued. Okay, so here clearly this infinite sum is absolutely convergent, and this operator is an element of the Banach space, the image. Okay, let's go to the main results now. Let's go to the main results. Excuse me 1 second, excuse me. Main results. F is continuous from AB to X. Alpha is between 0 and 1, so that n to 1 minus alpha is greater than 2. Then we have that the error quantity A and F x minus f of x is smaller or equal to this number times twice the modulus of continuity with speed 1 over n to the alpha plus the norm of f subnorm over this number. And of course, the uniform norm is smaller or equal to the same number called lambda 1. Clearly, the limit of A and F is F pointwise and uniformly. Let's see how this proof is done. The norm of this error quantity is smaller or equal to the sum of the norms, and then you split into two parts, k over n minus x smaller or equal to 1 over n to the alpha, or k over n minus x greater 1 over n to the alpha, and you estimate this k over n minus x is smaller 1 over n to the alpha. This thing is smaller or equal to twice the subnorm of f, but all this is less than 1. So also this is less than 1, and you come up to that. Finally this, and that gives the proof. Okay, that gives the proof. One more time, what I proved. Let's see the theorem. Here is the theorem. It's nice. I mean, here we don't assume any differentiability, and the proofs are short and nice. And the speed here is 1 over n to the alpha of the whole thing. I mean, this goes much faster, much faster to 0. So the sum goes with the slowest speed of 1 over n to the alpha, usually. Okay. Continuing. Let's go now with the quasi-interpolation operators. Let f continuous and bounded from R to X, alpha between 0 and 1, so that n to 1 minus alpha greater than 2, and you have the estimate of the error quantity of approximation smaller or equal to this. Okay? Again, if f is continuous bounded, we have pointwise and uniformly convergence. All right? So this modulus to go to 0 needs f to be uniformly continuous. Okay, The proof is similar. This f of x, you multiply by 1, which is this. Here is use the partition of unity we discussed earlier, and then putting things together, splitting the infinite sums in two parts, the greater than 1 over na and the smaller equal 1 over a, and it's done. Okay, now we want to move on and involve differential functions. The x value Taylor formula in an appropriate form is this, which I use. Usually this integral here is a Bochner type. Okay, so I don't want to go into details on that. I'm going to the theorem. Okay, let f n times continuous differential from a b to x, and nm natural numbers alpha between 0 and 1, and n to 1 minus alpha greater than 2 always. Then what's going on here is the following. A and fx minus f of x is smaller or equal to this number times the sum, norm of the derivatives, times this zero quantity here. I calculate exactly all zero quantities. Times that, the modulus of continuity, and this zero quantity here. Okay? If you assume initial conditions, the n derivative 0, then you get this, which is nice and compact, you know. Okay? Modulus of continuity with speed 1 over n alpha, and outside you have 2 over n a n, so the speed is going to be n to a times n plus 1, uppercase n plus 1. Usually this does not count. You go with the slowest speed of the two. And then you can have the uniform norm. Same thing, just take the derivative, the subnorm of the derivative. So again, I have limit of a and f to f pointwise and uniformly. So the next leap is going to be mix up things with fractional calculus, Caputo fractional calculus. Just to remind you, let A be subset of real numbers, X Banach space, alpha positive, M is the ceiling of alpha, F from A, B to X, Fm is L1, the M derivative is L1. We call the Caputo-Bochner left fractional derivative of order alpha, this Bochner integral. It's similar to the real case, okay, the analog. Okay? So this derivative exists almost everywhere, and is L1, and if Fm is L infinity, then I get that the derivative is continuous, and also the norm of the derivative is continuous. Nice properties. So this is the left-hand side derivative. In fact, has the property at alpha is 0. If f is Cm minus, it has many nice properties, just mention one here. If f is m minus 1 continuous differentiable and fm is L infinity, then f alpha alpha f, this is A, this is alpha, the order. The order is alpha, A is the anchor point. At A is 0. Okay. Next comes the right-hand side fractional derivative. You see, for years I did not know, and I was trying to do approximation theory only with the left-hand side derivative, but apparently I needed both left and right to achieve the convergence of error quantities to zero. So let me introduce the Caputo-Bochner right fractional derivative order. A alpha is similar to one you know for real valued functions. Again, has nice properties. Exists almost everywhere. Is L1. If Fm is L infinity, then the fractional derivative is continuous, and the norm of the fractional derivative is continuous. And again, the fractional derivative anchored at B is 0. So regarding the right-hand side fractional derivative, Caputo type. Apparently, the Caputo type is the dominant in nowadays for doing lots of good things in mathematics. I just wanted to mention the Taylor formulae, fractional Taylor formulae. Let F natural number, FCM. Then you have the left fractional Taylor formula. Here you have fractional derivative. In the right, fractional Taylor formula, this one. They are used a lot in approximation theory. As a convention, for x less than x0, this is 0. For x greater than 0, the right-hand side derivative fractional is 0. And now come, okay, let me mention that too. If f is n minus 1, continuous differential, fn L infinity, n is the ceiling of nu is the fractional order, then the fractional derivative is bounded, the modulus of continuity is bounded, all are nice, you know, modulo of continuity is bounded. So keep in mind these two. F C m minus 1 continuous differential. Fm L infinity. M, the ceiling of alpha. Alpha is the fractional order, is not a natural number. Then the moduli of continuity and the sup of moduli of continuity over the interval x0b, x0 runs in a b, they're finite. These two are used in the proof of the next result, these two, 92, 93. So these are finite. Okay, now comes the x-value fractional approximation result by neural networks. Very lengthy. The proof is huge, about 10 pages. I skipped it, but I think it's interesting. So let's read it. Alpha positive n ceiling of alpha, alpha not a natural number, f, c, and a, b, x. And b between 0 and 1. This b now takes the role of alpha when I don't assume differentiability. So b is the alpha we talked so far. And alpha I named the order of fractional differentiation. Okay, the first result goes like this. A and fx, these are the operators over compact interval minus this sum, derivatives and operators on this function. This is the function dot minus x to the j at x. Smaller equal is a number, the gamma function plays a role, and I have the moduli of continuity, left-hand side, excuse me, right-hand side, left-hand side, and over n to a alpha beta, plus this number here, times these fractional derivatives, subnorms on the interval ax and xb. If you have initial conditions, the derivatives, ordinary derivative 0 for j1 to n minus 1, I get this result, direct consequence of the previous. There are the two moduli here and this kind of residual remainder estimate. Okay? And then, if I want to write down the whole thing, is this. A and fx minus f of x, smaller or equal, the derivatives here, the zero quantity here, all goes to zero. Okay, everything goes to zero. There is convergence. So everything is calculated exactly. I like to calculate things exactly. I avoid big little o. And if you take the supremum norm, same thing, but the derivative has here supremum norm. Okay, if uppercase is 1, then the sum is 0. So again, we have fractionally pointwise a unit convergence with rates of an to the unit operator. As I said, I'm not going to give the proof. I'll tell you what tools I use. First of all, d alpha x minus f of x and d alpha star x f of x is 0. That's a great tool. And then the two Taylor formulae, the left-hand side, I mean, you need to write them down in the appropriate way to do the theorem, and the right-hand side. And I do work with that, you know, I multiply with the activation function, etc., etc. Okay, let's go now to see things in a nice way. And a direct application of this fractional, long fractional theorem is when n is 1. That means the fractional order is between 0 and 1, which is typical. Then f is C1, and 1 minus beta is greater than 2. Again, beta takes the role of alpha when I don't assume differentiability. Is smaller or equal this is a number constant, the modulo of continuity over n alpha beta. Plus this quantity here, this zero quantity here. You see the estimates now have taken a more compact form. The big sum has disappeared. And then if I take the infinite norm, I have this nice result here. But I'm going to get more specific. I'm going to assume fractional order 1/2, alpha 1/2, and write the previous result, theorem 31 to corollary 32, in this nice way. A and fx minus f of x smaller or equal the constant, or the square root of pi. Here the fractional derivatives of order 1/2, okay? And that. And the sup norm gives this. So we are going to use this result here, 148, to make a convergent analysis and see that adding order 1 differentiability, ordinary derivative of first order to f, makes the convergence faster without the assumption of any initial or boundary condition. That's the big thing in this paper, if it is big thing. Okay, so we are going to assume for convenience that the fractional derivatives are of Lipschitz type. So we have these Lipschitz inequalities by assumption, which is not really strange. They use that all the time. And then this part of the inequality 148 is smaller or equal of a constant k, which is k1 plus k is 2, the ellipsis constants, over n to the 3 beta half. Let's see one more time, 148. Excuse me, 148. It has the constant, forget about the constant, has the some modular continuity over n to the beta halves. Again, this is a constant, I mean zero quantity, goes to zero. And these fractional derivatives, I mean subnorms. You don't worry about them, it's a constant. So you worry about the modular continuity, the speed here, n beta halves, and also this speed here. And n minus beta minus 2 to m. Okay? This is what you worry. Working on 148. So the other sum under 148 is basically a constant L over n 2m 1 minus beta. Okay? So the speed 148 goes to 0 is m over minimum of these two speeds. Always we go with the slowest. The prevalent is the slowest speed in a sum of speeds. Okay? And we distinguish two cases. In here, we rewrite this 152. Is that if beta is between these two numbers. And the speed of convergence would be 1 over n to 2m 1 minus beta. And is this when beta is between 0 and 4m over 3 plus 4m. And the speed in that case is 1 over n to 3 beta over 2. Now, from the first theorem I proved today, as I said, I'm replacing alpha there in first theorem 11 I proved by beta. The speed over there is 1 over n to the beta. So beta is between 0 and 4m over 3 plus 4m, which is smaller than 2m over 1 plus 2m. So they have the same interval here, beta in this, in 154, and beta here in the original theorem, first theorem. So the error quantity goes much faster to 0. And this comes, of course, because we assume differentiability of f, of order 1. And no initial condition was assumed. Okay? So, again, the speed without differentiation is 1 over n to the beta. With order 1, get at least speed 1 over n to 3 beta over 2, which is higher speed than 1 over n to the beta. So with methods of fractional calculus. Proving that fractional calculus is helpful to other areas of mathematics. Okay, another little thing to finish the lecture, I use iterated or consecutive fractional derivatives, same thing. I call dxn plus 1 alpha f, any of the two, left or right. And the modulus of continuity, the max of these two. And then, from my books, I let alpha between 0 and 1, f from a b to r, f prime L infinity, x fixed. The iterated derivatives are continuous, and I have initial conditions, of course. So right and left iterated fractional derivatives are continuous with initial conditions. Then I have a general theorem for f estimate. This nice 158. Okay? And then if I pass on the operators A and F minus F, I get this result, modulus of continuity, delta positive, any delta positive, times, so the zero quantities are these two sums. All these go to 0. So I have lim A and Fx goes to 0. using now the iterated fractional derivatives. The proof is not really difficult, you know, it's just using the basic result I mentioned before and having the proof. Let me give the corollary, much makes compact things. A and f of x minus f of x is the constant, the modulus of continuity of the iterated derivative of f. This is a constant over gamma to a constant, and the zero quantities are these, the two brackets here. So the whole thing goes to 0. I'm almost done. Talk about the references. Here is my first paper, 97, in Journal of Mathematical Applications. One of my early books, 2001, where I have there also these results. The multivariate theory, no, this is the tangent neural network approximation, yes, 2011. Sorry. Hyperbolic tangent is preferable because it also takes negative values. And they use it in convolutional neural network theory. It's more attractive than the standard sigmoid 1 over 1 plus e to the minus x. Other books of mine and papers. And here is a paper that inspired me a lot, Chen and Chow, approximation operated with sigmoidal functions. And then some very important books, Haking, Neural Networks, Comprehensive Foundation, McCall repeats the one I talked earlier, Mikuzinski on Banach, Wagner integral, Mitchell machine learning, and last but not least, this famous little book by Silov, Elementary Functional Analysis in Dover. This has been of great help to me. So I think I'm done. Excuse me one second.
Okay, thank you very much for this
My pleasure.
detailed talk. So are there any questions or comments? People are a bit tired. It's been a long day.
Yeah, sorry for that. It's the time, you know, I'm United States and it's 1 p.m. now here. Convenient time for me, you know.
Yeah, but
thank you for helping me to give lectures at good times for me. And sorry for, I know you are tired.
It's okay. So, well, let's thank the speaker again. And see you next Monday for more talks. You're giving another one, no? Next Monday?
Yeah. We'll be on a different topic on fractional calculus in Banach algebras, okay? So it'll be totally different, okay? Thank you so much for coming, and we should be safe and everything to be peace on earth, okay? Bye-bye.
Yeah, bye-bye.